My name is David Ashpole. You can reach me at Dashpole on GitHub or Slack. And today I'm going to be talking about Node Allocatable. Node Allocatable is a feature that SIG-Node introduced in version 1.2 of Kubernetes and finished in version 1.6. I work for Google on the Kubernetes project and have been for a little over a year. And I attend SIG-Node, and this is a project that SIG-Node worked on. So, Node Allocatable, to start it off, has two main components. The first is honest resource accounting for node overhead. And the second is that it provides protection for system daemons. And the problem that Node Allocatable solves is that we have a node and it has some capacity, but really some of that capacity is consumed by overhead. So let's say we have 1 gigabyte of memory. We aren't actually able to fill that entire gigabyte of memory with user pods because some of it is consumed by Docker and the kubelet and other operating system daemons and the node problem detector and what have you. So in this case, if we were to schedule pods, and let's assume that for now the pods use exactly what they request. So we schedule pod 1, we schedule pod 2, so far so good, but we schedule pod 3, and all of a sudden we have an And this is not desirable because the node, because when pods request resources, what we're assuming is that if I request 500 megabytes of memory, I should be able to actually use 500 gigabytes of memory, megabytes of memory, without suffering consequences such as an kill. So this is a really bad scenario. And the way that we fix this is by we introduce this feature that allows you to reserve a portion of the node. And let's for now assume that we're perfect and we're able to reserve exactly what the overhead is. In this case, instead of encountering a system what we would end up with is just a pending pod. And I'm going to give you a quick demo just to show you how you can inspect and take a look at and play around with Node Allocatable. So I'm on Google Compute Engine, and I'm going to go to the Kubernetes engine and connect to my little cluster. It has a single node and a pretty small node, 1 CPU and 3.25 gigs of memory. Oops. So I can see that the node reports a capacity. That's pretty much exactly what the VM I got on Google Cloud is. It has 1 core and a little over 3.25 gigs of memory. But my allocatable is less than that. I only get 940 millicores and 2.7 gigs of memory. And what allocatable is it's the space for user pods. And the reason why, this is on version 1.8.4, the reason why that allocatable is set to less than the capacity is because built into the node configuration is the assumption that some of the node is used by overhead. And for this node that I've picked out, this small one, it looks like the overhead is about 40 millicores of CPU and something around a gigabyte of memory. And down at the bottom here, I can see that Kubernetes is keeping track of the amount of resources that I've requested compared to the allocatable of the node. So I can see that we've got things like Fluentd and Heapster and kubedns, and they all have some requests for CPU and memory. And those amount to most of the CPU, but not very much of the memory. So I've created this little simple pod here. It's in a deployment, has 1 replica. It's just a BusyBox pod that does nothing, but most importantly, it requests 1 gigabyte of memory. So if I create this pod, Let's check it out. Okay, so this pod's running, and now if I describe the node again, I can see that now this has been updated, and instead of using 27% of my memory, or requesting rather 27% of my memory, I've now requested about 66% or 1.8 gigs. And it looks like I should only have about 900 megabytes left, so if I tried to scale this, to add a second replica, I see that the second pod is pending, and actually it's never going to be running, because let's check out my events. And for this pod, I've got a failed scheduling event, actually a whole bunch of them, 6 of them. And it says that the reason why it failed to schedule is because there's insufficient memory. So as we can see, the way that the scheduler works is before it schedules a pod to a node, it first checks to see that the total requests are less than the allocatable. So because there wasn't another gigabyte of allocatable memory on my node, the scheduler doesn't schedule the pod. And so I'll just clean up after myself. And we'll head back to the slides. So, and the reason why, to get back to what I was saying earlier, the reason why honest resource accounting is actually useful is because every pod that's scheduled in the second scenario is actually able to consume its requests without suffering a consequence such as an kill. And this is desirable because this third pod that I tried to schedule may end up being scheduled on a different node, or if there aren't nodes available and you have cluster autoscaling enabled, it may create another node to be able to schedule this pod, or something else. So this is a failure, but it's not nearly as bad as scheduling it to a node where it isn't actually able to consume the resources that it requests. And this provides kind of a consistent environment for your pods. It shouldn't matter which node your pod lands on. It should always be the case that your pod is actually able to consume what it requests in terms of resources. So the second part of Node Allocatable that's important, and arguably even more important, is preventing resource contention. Now, for CPU, it's a little hard to demonstrate because when things compete for resources for CPU, things just get throttled. So if you were to consume all the CPU on your node and starve your operating system and the kubelet and Docker of CPU, things would just slow down, and your node might go not ready for a couple minutes, but as soon as CPU contention was reduced, your node would go back to normal. But for memory, it's actually a much bigger deal. So the way that we enforce that we limit resources in Kubernetes is using C groups. So I'm denoting the node limit with these brackets, and then there's also pod limits, which is introduced as a C group here and has the same limit as allocatable. So we've introduced this extra C group here, and what we'll see is that, at least in this case where overhead is less than we reserve, over here, if pod 1 uses more memory, what you end up with is a system oom. And the important thing to note about a system oom is that when you run out of memory, the oom killer chooses among all of the processes that are contained within this limit, so in this case every single thing on the node, it chooses some process to kill that's consuming memory. So the kubelet is a candidate, your pods are candidates, Docker is a candidate, operating system processes are candidate, and so on. And this is fairly dangerous because if something critical dies on your node, then oftentimes it's not recoverable. But in this case, where let's say pod 1 consumes a little bit more, we've exceeded this C group here, but we haven't hit the system C group, or the system limit rather. So what we call this is just a C group oom. And this is far less dangerous, at least for your cluster, because what will happen is that a pod or a container will die, and Kubernetes, because it's self-healing, will eventually hopefully bring it back. But because this overhead here is not placed inside this C group, it's not a candidate. So all of your operating system daemons, the kubelet Docker, they're all safe from the killer. And so a C group is much more preferable to a system And now I'll demonstrate why. Now for the fun part. This is a demo that should hopefully show you why you should care and why this matters for your production environment. So, I've created 2 clusters here. One I've named disabled and the other I've named enabled. And they're using the most recent version with 2 small nodes, one in each cluster. So first things first, I want to change them from the default configuration. So going to SSH into each of them. Let's see, this is the disabled one. So going to change the kubelet configuration. First thing I want to do is, for the disabled one, I'm going to remove the memory reservation, and I'm going to disable memory eviction. So I've done that, and then I've removed the memory flag from eviction. Okay, that's good. Okay, and now for the enabled one, I want to leave the memory one alone, but I still want to disable memory eviction. So on this one as well, I'm going to remove this from the eviction flag here. And then I also want to add one more flag. Okay. And make sure I did everything right. Let's check the log. That doesn't look like it's right. Oops, that's the one I want. Okay, that should be good. Okay, so let's see what we've done here. So now I'm in a cloud shell. Let's switch to my enabled cluster, make sure that everything's good. Okay. Make sure I still have allocatable enabled here. As I can see, it looks like I've got about 960 megabytes gone from what I'm able to use for pods. I'll switch over to the disabled cluster. Describe that just to make sure that, yep, indeed, I have disabled Node Allocatable, and the entire node is available for pods to use. So, first things first, let's check out the pod I'm going to use for this experiment. It's using our stress image. It has a single container with the stress image. I've configured it to use 20 gigs of memory, which should obviously cause an before it gets there. And it consumes 100 megabytes of memory every second. So, a pretty evil pod, all things considered. Let's create it, and then let's switch back to the other cluster. Enable. And create it there too. Switch back to disabled. And now let's watch our pod. So it's running, and hopefully in the next couple seconds what we should see is that it'll cause a system oom. Okay, there it is. Let's check out our events and see what we can find. Okay, so we have two events here. One is called oom killing, and the other is called system oom. And these two events exist to let us know that, one, our stress container was killed, and two, there was a system oom. And the reason why it tells us that there was a system oom, in addition to letting us know that our pod died, is because system ooms can be dangerous, because every process on the node in a system oom is a candidate for the oom killer to kill. Okay, so let's delete this memory pod here, and let's go check out the enabled cluster to see if there are any differences. So this one's, whoops, that's what I meant to do. This one's already been restarted twice. And let's see what kind of events we have. So a ton of oom killing events, but no system ooms. So what we can see is that Node Allocatable did its job. As I explained before, we hit a C group, which is the pod C group, instead of hitting the system limit. And so even though we have tons of oom killing events, that's fine, because the node is still safe. The kubelet was never something that could have been killed. Docker was never something that could have been killed. And that's preferable to the alternative. So that's... Okay, let's delete that. Delete all the events just so that we're able to see the next part of this easier. Okay. Now let's edit this pod, because right now it's malicious, but it's not that malicious. A single pod can wreak some havoc, cause the system oom after all, but what we really want is we want lots of system ooms. So we're going to make this, we're going to increase the replicas to 20, change the amount that we are using every second to only 10 megabytes, and decrease the total memory to 200 megabytes. And what this does is it makes a whole bunch of pods that each use a little bit of memory. But instead, when the oom killer wakes up and kills something, it'll kill one pod, hopefully, but then within seconds, another pod will cause an oom, and then another pod, and another pod. And we are constantly allocating a ton of memory from all pods. And pretty soon, we should be able to see the difference when under a ton of pressure between using Node Allocatable and not using Node Allocatable. So let's give it a shot. Or wait, let me see. We are currently on the disabled cluster, and I want to actually switch over to the disabled cluster, or sorry, to the enabled cluster. Okay, we'll create it, And then we'll leave that be for a while. We'll switch over here, create it here as well. And we'll see what happens to our pods. So right now we've got 20 of them, and they should all be creating at the same time. And now they're running. Okay, and pretty soon that should be all of them, I think. So, it shouldn't take too long, and eventually we should see the node get under memory pressure. So let's actually watch the node instead. Get the node. Let's see what happens here. So what should be happening is that all of the pods are consuming a little bit of memory at once, and then eventually the node will run out of memory and it'll kill them one by one by one. But it looks like the node is gone, not ready. Let's see what we can find around here. Why is the node not ready? Let's see, I don't see any. Let's see, everything's gone unknown, so it doesn't actually even look like we've. Let's see if we even have no events. Wow, so the node died so quickly. The node must now be in a very bad state. It's a bunch of conditions are unknown. Kubel has stopped posting node status. We could try an SSH into here, but I doubt that will be successful. And basically, what this shows is that when you have a bunch of things that are causing memory pressure and the node is under a lot of stress in this way, that it is super easy to just completely wipe out your node. This node is non-functional, probably will be non-functional, and there's likely nothing we can do other than delete it and start over. Okay, I'm just going to leave that running. Okay, but that was in the cluster where it was disabled. So let's switch over to the cluster where it was enabled. And see if we've fared any better. So, node's still ready. Got a couple events. Looks like they're happening once every couple seconds, but they're all kill events, no system ooms. Looks like some of them have been killed, but other than that, the node looks completely healthy. Yep, it's ready. Still posting node status. Doesn't appear to be having any problems at all. In fact, I still have this request pod here, so let's see if we can create a pod. Looks like it's creating. Oops. So let's watch this pod and see if it actually becomes running, even though there are a whole bunch of malicious other pods on the node. And maybe while we're waiting for that, we can check back with this. It is still not having any luck. So at this point, we can pretty much give up on this node. Let's see, it's disabled. So if we wanted to fix this cluster, we would probably just go here and delete the node, and Kubernetes will recreate it for us. But you know, it's a node that we have to toss out, and any workloads that were running on there, any data that was running on there, is now completely gone and irrecoverable. Even if you had persistent volumes or something on there, they would no longer be persisted. So cool. On our cluster with Node Allocatable enabled, we were able to create another pod and get it running. And that, I think, demonstrates in really practical terms that when your node comes under memory pressure, whoops, it was killed. When your node comes under memory pressure, you really want to have Node Allocatable enabled. It makes a world of difference to have cgroup ooms instead of system ooms. And I think it really demonstrates the value of this feature. The last thing I want to revisit before I finish is what happens if we don't set the amount that we reserve equal to our overhead. And realistically, that's probably never going to happen, right? At the very beginning, in my slides, I always set them equal, but usually we're in one of two cases, which is either we're using less than we reserved, or we're using more. And so in this case, where we're using less, we end up wasting a couple resources, right? And while this isn't great, we think the benefits are worth the cost in terms of making your cluster more robust and giving your pods a more consistent running experience. And when we're too low, we do reintroduce some resource contention, right? It is possible here that if every pod is using exactly their requests, then someone could end up being unkilled or evicted because of this overhead. But the important thing to note is that the amount that we're in effect overcommitted by is quite small, making the odds of something like that also very small. And even though this doesn't solve the problem that we set out to solve, it mitigates it in a huge way. It means that only in very, very rare cases will you end up with pods that are using less than their requests, experiencing some sort of negative side effect of this. And there's one more topic I want to cover, which is you may be running on-prem, or you may be running in a different cloud or on Google Kubernetes Engine. And if you're running on Google Kubernetes Engine, great. We've already set this value for you starting in 1.7.6. And we did a whole bunch of data collection across all of the clusters on GKE, and we had some interesting findings. First of all, you can notice here, this is in the documentation for cluster architecture on the GCP docs. So you can take a look at these yourself later if you want. But it's important to note that, for example, on the smallest node that I would recommend running on, we reserve a full 700 megabytes of memory out of 1.7 gigs, which is probably something like 40%. Seems ridiculous, but that's because you're running a full Kubernetes node with Docker and Kubernetes and monitoring and the node problem detector and an operating system. And it turns out that those just running have non-zero memory usage. But if we take a look at, for example, the highest memory node that we offer, which is here, it's actually only 15 gigs seems like a lot, but on a 416 gig machine, it's actually not that much. It's only 3 and a handful percent. And so one of the conclusions I want to draw from this is that Kubernetes, while you can of course run it on really small nodes, that there is definitely a benefit to scale here. That this overhead that I've been talking about is a much bigger deal when you're running on really small nodes than when you're running on large nodes. And so rather than running, for example, hundreds of N1 standard ones, if you're on GKE, you might want to instead run a handful of N1 standard 8s or N1 standard 16s, because the benefit that you get is that the overhead compared with the capacity of the node goes down by a lot, which is what we've noticed from our data collection. Now, if you're not running on Google Kubernetes Engine, and you're just running vanilla open source Kubernetes, then this isn't, Node Allocatable isn't enabled by default. And what that means is that it's actually set to 0. So what you can do, and what I'd recommend, is I'd recommend that you turn this on for your clusters, because I think there's an enormous benefit, and it should make things more robust. And you have a couple options for how to decide to set these values. A great starting place may just be the values that we've published here. So if you've got nodes that have, about 15 gigs of memory, maybe try reserving 3 to start out with. The other thing that you can do is just, because every workload is different and it uses the components more or less, if you're constantly spamming our stats endpoint or something, then we're going to have higher usage. But if you're not, then maybe you can reserve less than we have on GKE. And so I'd recommend just taking a look, using whatever monitoring you have, and seeing how much Docker and kubelet and other things, just seeing what the resource consumption is, and setting it based on that. And yeah, I think that's all I've got for today. Thanks for watching.